Okay, hello everyone. Before I start, it's a pleasure to be here. Thank you for the invitation. My name is Daniel Canedo, and I'm a researcher at University of Aveiro. And today I bring you a brief presentation about how to uncover archaeological sites from aerial imagery using vision transformers. Um, so this is the outline of my presentation. I will start with the motivation for this work, the challenges that we faced, all the data engineering, the proposed system, the results that we obtained, and finally, future directions. So it's important to contextualize the technology that we use. We utilize the vision transformers that are not large language models, but they utilize the principles of LLMs. So what this network essentially does is dividing the image into fixed size patches, and you can see these patches as words in a sentence, and the sentence being the whole image. And these patches have meaning within the image and also a position. And those two things are quite important for the transformer to learn all the relationships between all these patches during the training. Um, so this work was done under the research project called Odyssey. And in this project, the main goal was to develop a platform for the archaeologists to use during their day-to-day work. And the work package that our team was working on was responsible for building a machine learning block for this platform so that the archaeologists could submit images and then this AI block would detect archaeological sites. And the archaeological site of interest for this work was the hill fort. And you can see here in this image what they look like. They are some kind of enclosures that do not have a defined shape, which complicates things for machine learning models to detect them. So some of the challenges that we faced, lack of publicly annotated data. So we had a lot of data, but they were not annotated. So we had to rely on the Atlas of Ilford in the UK, and we also had to rely on the knowledge of our archaeology team. This problem is prone to false positives due to the aerial perspective of the data. Since the perspective is top-down, we can only see the top part of the archaeological sites, and this top part is easily confused with any other element in the landscape. Not only for machine learning models, but also for the expert archaeologists that do these kinds of digital surveys. The data is quite heavy, which causes processing and storage challenges, and it's an emerging area in computer vision. It doesn't have many publications that we could inspire ourselves on. As for the data collection, our archaeology team did some LiDAR surveys here in Portugal, and we also collected some publicly available LiDAR datasets from Portugal, Spain, and the UK. Um, the LiDAR data is essentially 3D point clouds, which are quite heavy on a computer. So what our team did was processing those point clouds to obtain a digital terrain model. That's what you see in the left side, which is already in 2 dimensions. Then we apply a visualization technique to obtain the local relief models. At the time, we did some state-of-the-art research and realized that this type of model was ideal for our case because it highlights micro topographies in the landscape, which makes it easier to detect anomalies in the landscape. And after having these local relief models, we essentially annotated them, annotated the hill forts that we knew about. After having the annotations, we had to build our dataset. As you can see in this table, the images that we have access are quite huge, and we cannot simply feed those images to our models because, of course, it will give some kind of memory or GPU error. So we had to break these images down into smaller images, and we built a simple algorithm to do that. This algorithm essentially iterates over all the annotations, generates random coordinates for a cropping window, and the cropping is done if it respects two main criteria. The first criteria is that the archaeological sites must be fully visible within this cropping window. And the second criteria is that there should not be archaeological sites that were already previously saved in another iteration. So we want to retain uniqueness in the dataset. Uh, when we had our data set ready, we could proceed with the training. The chosen model was called SimiX, which is a vision transformer. And this vision transformer is capable of fusing two types of data, RGB type with another type for semantic segmentation. This was ideal for our scenario because we wanted to replicate what the archaeologists already do in their work when they do those digital surveys. They have in their monitor a lot of different types of data, and they search for the archaeological sites on those types of data because different types of data do have some advantages and disadvantages of over the other ones. And in our case, we had our local relief models that highlights the microtopographies, but we didn't have the rich information from the satellite images. So our goal was to fuse these two type of complementary data. And then we proceeded with the training, and you can see the results of that training in the graph on the right. After having the model trained, we built our pipeline. We start with the local relief model tiles where we want to deploy our model. With a sliding window, we sweep through all those tiles. This sliding window has real-world coordinates. With those coordinates, we are able to do a web map service request to obtain the satellite image, and then we feed those two images on the model. Then the model produces some inferences that are filtered by a post-processing block to filter obvious false positives, and then we have our final inferences. After that, we do a human in the loop process where we have our expert archaeologists to analyze those inferences and say, okay, this is an obvious true positive, this is a false positive, this I'm not so sure, and so on and so forth. And with that feedback, we are able to enrich our dataset with more images and retrain the model. So what we are essentially doing here is basically guiding the model in this difficult task of distinguishing between what is an actual archaeological site or another random element in the landscape that happens to have a similar shape. So this is the digital validation that our archaeologists do. I put here an example. We built a small script that presented our expert archaeologist with two images, and then he could analyze the inferences that are in those images. And just a curiosity, in this image, the left inference is a true positive, and in the right is a false positive. It's a football field according to our expert archaeologist. So as for the results, with this human in the loop approach, we were able to reduce false positives by 99.3%. So we reduced it from 5.6K false positives to only 40 in Altumini with just one iteration of this human in the loop approach. And these false positives, by the way, they are not they can actually be archaeological sites. We call them false positives because they are not annotated, so we consider them false positives, but they will be analyzed by the archaeologists to see if they are actually false positives or if there are something there. So we also discovered ill forts that were previously unknown to archaeologists, and the proposed solution at the time, which was 1 year ago, achieved state-of-the-art results. So the uncovered ill forts, we found 9 potential ill forts in Jerez and 768 potential ill forts in the UK. I say potential because they were digitally validated by the expert archaeologists in our team. However, they still require fieldwork validation to well, to confirm that they are actually Ilfords. And in these images, you can see they are in the UK. The one that has a red dot is a known Ilford in the UK, but the other two are not known. But our team is almost certain that they are actually Ilfords. As for the limitations of this approach, it has an high computational cost and long processing times. Uh, Processing data for the whole UK on a high-performance computer took around 30 days. The main bottleneck being the web map service requests, because we had to wait for the images to arrive, and also we could not make many requests because we could be timed out. Model fine-tuning is required when applying to regions with different site typologies. The model was firstly trained on Spanish and Portuguese data, and then when we wanted to apply the same model to the UK region, the performance dropped because the landscape in the UK is quite different, and even the Ilfords are also a bit different from the ones we have here in Portugal and Spain. And the last point, we still require an expert archaeologist to validate the inferences from aerial imagery in that human in the loop approach. This is a difficult task for the archaeologist because he has to validate thousands and thousands of inferences, but this step is crucial to obtain a good result because we still need this collaboration between human expertise and AI to improve the results. As for future directions, we want to explore archaeological predictive modeling to identify regions with higher archaeological potential. So instead of applying our vision system in the whole data, we want to focus on regions with higher potential. That would allow us to reduce the processing time. And also we want to explore visual foundation models. In these three images, you can see it's from a work that was published last month. It's quite recent, and they utilize the visual foundation models to detect archaeological sites. And as you can see, these models are able to provide a reasoning for why they detected what they detected. And also they do not require training, as the previous presenter said. And that's it for my presentation. If you have any suggestion for our future work that we expect to continue in the next year, or if you have any questions that I'm able to answer, go ahead.
Thank you, Daniel. Are there any questions from the audience? Yes.
Hi, Daniel. Can I ask you a question?
Sure.
You said as part of your workflow, when you do this cropping, okay, you try not to crop. You want the entire archaeological site to be in the crop, but also not duplicated in any other crops, right? How do you do this? How do you do this drop out of the duplicated crops?
Basically, we iterate over the notations that we have, and then we generate coordinates, random coordinates, and we build a cropping window based on those coordinates. If that cropping window doesn't respect any of those two criteria that I mentioned, then we generate another set of coordinates, and so on and so forth until those two criteria are met. So you can imagine that this yellow window is like moving, trying to search for a position, ideal position to make the crop. And it does this to every single annotation that we have. And with that, we are able to retain uniqueness because we don't want, obviously, to have duplicate annotations in our data set. I'm not sure if I answered your question or...
No. Understood. Thank you.
Okay.